Okay, so the last thing we're going to be looking at in chapter 8 is solving rational equations. So it will definitely bring up some of the different concepts we've seen. Like one thing that's going to be common in these is we're going to have to find a common denominator. So we can kind of basically multiply it out. Um, but basically, a rational equation is just any equation that contains at least one rational expression, basically fractions. So, and most likely you'll be solving for a variable either in the numerator or denominator of one of your fractions, potentially. Basically, the goal when you're solving a rational equation is usually to either get a common denominator for all your fractions. So basically, you can eliminate that denominator because the idea is if I have something like say I had something like oops, sorry about that. If I had something like this, I won't do 2 over 2 because you might be tempted to simplify. Like if you have everything over the same common denominator, I can multiply both sides of this equation by 2 because and basically what that's going to do is I can get rid of my denominator. So like I would just have what the numerators were, 1 plus 3 equals x, and obviously that would be 4. So if you get a common denominator, basically you can just eliminate it or get rid of it from all your fractions. So that's really the goal with these problems is to get a common denominator so we can get rid of all of our fractions essentially. After we've done that, we'll collect like terms, solve for the variable, just like we've seen. One thing to keep in mind with these rational equations, just like other like radical equations and other types of equations, you need to be careful for extraneous solutions. So, and this is really going to be true if you're multiplying both sides by an algebraic expression. If you're multiplying like both sides of an equation by like something with an x, you really need to make sure you're checking for these extraneous solutions. I mean, if you're the solve, if you're just multiplying both sides of the equation by like 5, like a single number, not a variable, you won't really create any, but you can always just check to be safe. So let's just get into some examples. We'll see how far we get with this today. But basically for this problem, you want to think about like we've got some fractions. We really want to think about what would our least common denominator be, or what would be a common denominator we could gain. So if since we just have numbers, I'm looking at 5 and 4. And sometimes there might be a smaller number you can think of, but one way to get a common denominator is just multiply those by each other. 5 times 4 would be 20. So both of those numbers are going to go into 20. But sometimes you might be able to think of a smaller one, but realistically, it's not going to matter. So what we're going to do is we're going to multiply both sides of this equation by 20. Because we're going to see basically this is going to clear our denominator. So, I mean, you can kind of do this in your head. I don't know if this makes sense, but if you multiply 20 to this first fraction, like 20 over 5 would be 4. Like maybe I'll write it like long ways. Like you probably don't really need to write all this out if you were actually working this out, but it's basically like you're taking 20 times both of these fractions. Obviously the right side is just going to be negative 40, but you could simplify this. Like if you divide 20 over 5, that's just going to be 4. So you'd have 4x minus 2 minus, and then 20 divided by 4 would be 5 times x minus 5. And then we could just solve this equation. So this, what I wrote here, you don't necessarily need to write this if you can kind of just simplify it in your head. But basically, when you multiply this by 20, think about how that's going to cancel out that bottom. Like what's it going to change to? But then if we just distribute, I mean, like this would be 4x minus 8. Be careful when you distribute the second one. Remember, that's like that negative. You got to distribute it to both parts. So minus 5x, negative 5 times negative 5 would be plus 25. Combine your like terms. So that would just be negative 1x plus 17. subtract that over, you'll get negative 1x equals negative 57. So divide by negative 1, basically flip your sign, you'd get 57. That's all said and done. If you I mean, like I said, we didn't multiply any variables to both sides. We just multiplied by a number. So, I mean, you could plug this in to see if it's extraneous or not, but you will see that it does work. It's really only when you're multiplying both sides. If you're multiplying both sides of your equations by like x plus 2 or x, like when you start throwing in the variables, that's where you really need to be careful. So let's look at B. The nice thing about the second question is you already have a common denominator. So basically the idea is like if you can't get a common denominator, or if you work towards getting one, basically you can just cancel out your denominators. Like, because really what you're doing to cancel that out is you're really just multiplying both sides of this equation by x plus 2. So obviously when you multiply this side by x plus 2, it just cancels out that denominator. Same thing on the right side. So basically, if you have a common denominator, like with fractions equal to each other, you can just eliminate them. So you just set the numerators equal to each other, essentially. And then you would just, since we got like a trinomial, we're going to hope this factors nicely. So you want to move everything to the same side. So I would just subtract the x over. I would add the 1 over as well. So I would have 0 equals x squared plus 1x minus 2. I want to see, does that factor? It does. You could do x plus 2x minus 1. So then if you just solve these, I mean, you would get x equals negative 2. You would get x equals 1. You do, since we technically, when we eliminated our denominators, we really were multiplying both sides by variables. So we do want to check these to see if they're extraneous or not. So if you plug in negative 2, and it can be kind of a pain sometimes to plug these in, I won't lie to you, especially when depending on how complicated. But so this first one, if I plug in negative 2, oops. Like if I plug negative 2 into the first fraction, I'm going to have negative 3 over 0. That's a problem. Like if you plug in negative and you get a 0 on the bottom, like it's not going to work. So this is extraneous for sure. Like I don't even have to plug it into the other side. And I guess that's really true. That's really more what you're going to be concerned about. Like what would make your denominator equal 0 with these extraneous solutions? That's really what's going to be the red flag. It's not necessary, because honestly, it's not usually going to be an issue. I can't think of it being an issue where it's not going to equal each other. It's really just going to be something that would be undefined in like the domain that would cause a problem. But if you plugged in 1, so the second solution we got was positive 1. If you plug that in, you're going to get 0 on the top. So it doesn't even matter. It'd be 0 over 3, but just 0 would be the left side. That's okay. You can have 0 in a numerator. So, and then if we plug it on this other side, we would get negative 3. Isn't that extraneous as well? The key says it's not, but if you plug it onto the other side, oh, wait, I did that completely wrong. If you plug in 1, you get 0 on the left side. And then if you plug it on the right side, you would get negative 3 over. Oh, wait, I'm plugging in 0. What am I doing? Okay, sorry. If you plug in 1 on the other side, that would be 1 plus 2 minus 3. Oh, yeah, you would also get 0. Okay, I was like, it does work. Okay. I was plugging in 0 instead of 1 on that right side of my brain for some reason. But if you do plug in 1, you're going to see you get 0 on the numerator for both of these. So you get the same result. And you don't get like a 0 in the bottom of your fraction. So there's not like any issues. So 1 would be the only solution. Eventually, we probably won't do it today, but later in these notes, I'm going to show you how you can kind of check these using a graphing calculator. So that could also be a way you could check for extraneous solutions, but sometimes with the graphing calculators, honestly, it's hard to get the pictures they give you. They're not super clear a lot of times. So sometimes you can't always depend on the graphing calculator, but it might also help you see if you have extraneous solutions or not. So some more examples. If you had something like x minus 12 over x equals 1, and we want to solve for our variable, we basically want to get a least common denominator, and multiply every fraction by it, basically to get rid of our potential fractions. So, I mean, all of these fractions are over 1 except the x. So, I mean, our least common denominator is just going to be x. I guess there's more than one way you could think about these problems too. Like some people think about multiplying it across. You really could just get them all over the common denominator and then eliminate them. Kind of depends on your thought process. That might actually make more sense for some people. But basically what we're doing is we are just getting a common denominator. So we're going to have to multiply everything by x. I'm trying to, should have thought about this more before jumping in. Let me just pause the video so this isn't like an awkward. All right, so sorry, I had to kind of like, sorry if this is like anyone's watching this video ever, and it's a little bit, I wanted to kind of think about it. I'm going to kind of switch my approach a little bit with these because I think it's going to be more intuitive from how you see it. So you want to figure out what your common denominator would be, and then basically just get all of these fractions that have a common denominator. So, I mean, so basically we'd have to multiply the first fraction by x and the second fraction by x as well. So if you do that, you would have x squared over x. The second fraction we didn't have to mess with because it already had the common denominator, equals x over x. And then from here, basically you can eliminate your denominators like we saw in that last question. So, I mean, really what you would be doing is multiplying both sides by x to get rid of them. But you would have, so now we would have x squared minus 12 equals x. We want to move that x over so we get like our trinomial. So we'd have x squared minus x minus 12 equals 0. I'm running too big. But that would factor to be x minus 4, x plus 3. So we would get our solution. So I'm going to just kind of write that up here. You would get x equals 4, x equals negative 3. But we do need to check if any of these will be extraneous. Oops. So if you plug in 4, you'd get 4 over 12 over 4. That would be 3. So 4 minus 3 equals 1. This first one checks out. No issues. The second one, if you plug in negative 3 minus 12 over negative 3, that would actually turn into a positive 4. That works as well. I mean, honestly, when you're plugging these in, I hope I'm not mistaken in saying this, but really you're not even interested if both sides of the, I mean, obviously both sides of the equations when you plug it in should be the same, but more what you're on the lookout for when you're checking these solutions, if you plug them back in, does it cause any issues? Like, are you going to get 0 on your denominator or something weird like that? But both of these ones work just fine. Let's look at the second example. So very similar question. You basically want to get all of your fractions to have a common denominator. Once they all have a common denominator, you can basically get rid of your denominators, set the numerators equal to each other. Basically what we did in question B. Like if you already had a common denominator, you can just eliminate it. Same idea. That's kind of our goal with these questions. So once again, our common denominator would just be x. So we don't have to mess with the second fraction, but the first and the third we do. So you would get x squared over x plus 6 over x equals 5x over x. You can just kind of get rid of this denominator. So you just have x squared plus 6 equals 5x. Very similar problem. You'd want to get it in that nice trinomial form. So that's why I'm kind of putting the x part in the middle. And this one would also factor nicely. It would be x minus 3, x minus 2. So you'd get positive 3, positive 2. You would want to just plug these in to make sure, but just for sake of time, both of these are true. Neither one of these are extraneous. And honestly, I mean, just looking at this problem, there doesn't look like, I mean, as long as you didn't get 0 as a solution, nothing's really going to cause any issues. But I'd have to think about it like more, but like I said, I really think the only thing you got to be careful about with the extraneous solutions in these is if it causes one of your denominators to equal 0. I don't think it's really a matter of if you plug it in, are you going to get 2 different answers? I mean, I guess maybe that could happen. So I don't want to like speak in absolutes, but from what I've seen so far, like I said, I don't want to think about it more, just to think of more, maybe if there's like a counter example. All right, so maybe for the last problem today, we'll look at something with a little bit more of a complicated denominator. So it's going to be a little bit more work, like maybe to get a common denominator between these three. So for this one, I mean, our least common denominator, and I will upload a key, so I apologize if anyone, if I mess up. I'm just going to erase some of this clutter. So I apologize. I'm sure there's at least one person still writing, but our least common denominator between these, basically, we're going to have to get both the x plus 1 part and the x plus 4 part. So for like this first fraction, I'm going to multiply it by x plus 4. For this middle fraction, I'm going to have to multiply it by x plus 1. For this last fraction, I'm going to have to multiply it by x plus 1 as well. So basically, my common denominators for all of these fractions is going to be this. And you don't have to like FOIL it out, because remember, we're going to just eliminate our denominator anyways. So it'd be honestly a wasted effort. But basically, we want to figure out what our new numerators will be. So for this first one, I just multiply, I have to distribute that x, so that would just be x squared plus 4x. For this one, I'm going to distribute the 3, so that would be 3x plus 3. For this one, I do want to FOIL this out. I got to FOIL x plus 3 and x plus 1. If you're not super good at doing that in your like head mentally, you can kind of write it on the side. But if you FOIL that out, you'll get x squared. You would get, oops, dang it. Sorry about that. You would, so sorry, kind of you'd get x squared, you'd get 1x, you'd get 3x. So together you would get 4x. And then 3 times 1 would be 3. Like I said, don't worry about the bottoms, because remember, we're just going to cross them out anyways when we're solving. So if you FOILed it out, I mean, you're still just going to cross it out. So we're going to set what we have. So we would just add these two numerators together. You could, if you want, you could already combine your like terms. We're going to set it equal to this. So this would be x squared plus 7x plus 3. One thing to notice, we have a lot of the same things on both sides. So what that means is basically your x squareds are just going to cancel. Like if you subtracted 1 over, they would just eliminate. Same thing with the plus 3s, those would eliminate. So really, we're going to have 7x equals 4x, which might seem a little bit weird. But the only way for that to be true is if x is 0. Basically, if you subtract this over, you would get 3x equals 0. Divide by 3, you're going to get 0. But I mean, like the only thing you could plug into like what you had here, the only thing that would make this true is if x is 0. So if you saw that, you could even maybe skip some steps. But basically, x would be 0. And you just want to double check. I mean, just looking at our original problem, like I said, I don't even, I mean, I'll think about this more. I don't think it's real necessary to plug it into everything. I could be leading you down the wrong road. But if you plug in x equals 0, it's not going to cause any issues on your denominator. So it is a true solution. I'll think about that. If I end up being wrong, I'll clarify that later this week. But like I said, I really think when you're checking for extraneous solutions, you're really only interested, will it cause an issue in your denominator? Like I said, I don't always like speaking in absolutes, because maybe there's like a weird example where that's not true. Like maybe there's a counter example. So I'm a little bit nervous in saying that. But like I said, from what I've observed in all the problems so far and just kind of thinking about it a little bit, I don't think you'd really run into other issues. But basically, this is the idea so far with solving rational equations. Obviously, you can get problems that are a little bit messier. You might have things that end up not factoring, or you might get higher powers. So like, I mean, it really depends on what they're throwing you at. But the goal is, like, the big idea is you want to get a common denominator for all your fractions, get them in that form with your common denominator, cross out your denominators once you have them all with the same one. And then from there, set your numerators equal to each other, use your algebra skills, your factoring skills to solve, and then just be careful with your solutions. Just make sure that if you plug them back in, you don't cause any issues. And the main issue, like I said, would be if you plug it back in, are you going to get 0 on any of the denominators? And if you do, that's extraneous. That's really what you got to be looking for. So stop the video.